welcome everyone. Today we have Peter Stone visiting us from UT Austin. He's also the chief scientist of Sony AI, and he's done some of the most exciting work in AI across robotics, machine learning, multi-agent systems. And for me, he's a huge role model in how to do great AI research from theory to practice. And so it's really exciting to have him here. The first time I met Peter, I was a PhD admit, and I fell asleep at my gate, so I missed my flight. 12 hours late to the UT Austin visit days, but Peter took time after hours to meet with me, and yeah, it's really wonderful to have him here. He's going to talk about some awesome work, and so yeah, take it away, Peter.
Good, thank you. Thanks all for being here. It's always a pleasure to be on the UW campus. I've been here several times before, but it's been a while. So. Thanks to Abhishek for inviting me. I've had some great conversations this morning already, and I'm looking forward to meeting with people more this afternoon. So I've got a lot to tell you about today, so apologies for a little bit of a whirlwind kind of talk. But I always have trouble thinking about what to talk about because I do a lot of different things in my lab. And so part of the talk is like really rapid fire, tell you almost nothing about a lot of things. But then I'm going to pick two things to really dive deeper on that are sort of telling you some of the technical details. So with that, I'll dive in. And they are human-in-the-loop machine learning first. The first part for robot navigation and the other for manipulation. Those are the two things. First of all, I'm at UT Austin, really exciting times there. Spurred by, we got one of the first NSF AI institutes. Now there's been many of those, but ours is on the Institute of Foundations for Machine Learning. Used that to found a machine learning lab headed by Adam Clivens. I've been very involved in sort of societal implications of artificial intelligence, both through the 100-year study on AI and also a project at UT Austin called Good Systems. I'm the director of Texas Robotics there. We had a ribbon cutting on a new space in 2021. We're going to host the Coral Conference in 2026. I hope all of you get to come and see it. Lots of innovations in AI education as well. I taught an AI literacy class for the whole university. We have an AI online master's in artificial intelligence. Happy to talk about any of those offline. This is some pictures of the robotics space that's in the old women's gymnasium when there was such a thing as a women's gymnasium. It's now filled with robots. This is just part of the space. And so I hope you all get to come and see it. We have now 17 core faculty in robotics at UT across 4 different departments. These are faculty who publish regularly at ICRA, IROS, and RSS. As I said, I do a lot of different things in my lab, but if you've ever seen me give a talk, probably you've seen this slide. The thing that sort of ties together all the research in my lab now and really over the course of the past 30 years is this question, which was also there in my PhD thesis defense, which is to what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains? And so that's led me to that sort of central question has led me to do work in autonomous agents, multi-agent systems. And especially what I'll focus on today, robotics and reinforcement learning. In my lab, I both do what I consider sort of bottom-up research, new algorithms and theory, and also more use-inspired or top-down research driven by applications. And so when I give a one-slide introduction to my lab, it's a lot easier to talk about the motivating use cases or applications that have driven the research. And so those have been things like robot soccer. And I was recently the president of the RoboCup Federation. These are some old Sony Aibo robots playing soccer autonomously. And now we've moved to humanoid robots. These are the nows. This is from a competition many years ago, but ours are the robots with their hands behind their backs, playing autonomously. Again, you have to remember that there's no human in the loop here, no remote control. They're sensing, deciding, and acting. They're working as a team, each robot controlled individually. We've had, here you see our robot going in on a breakaway. We've had to program them to walk, to kick, to coordinate. This was in the finals of a competition against a team from the University of Bremen in Germany that had won. They were the defending champion, but we ended up. This was the first goal of the competition. We ended up going on to win the game 4-2. And when we went back to Texas, they lit the tower orange for us, which they usually only do when the football team wins. So we were very honored. I've also worked a lot in general purpose service robots. So if you come, we have to our lab, you'll often see robots like this one just sort of wandering through the hallways. And actually, rather than showing that video, it's also a part of RoboCup. There's a RoboCup at home, and I encourage those of you who are interested in just general purpose service robots that could be in people's homes, interacting with people. RoboCup at home is a fantastic competition. Here's one of the tasks where a robot has to go into an arena, talk to a guard that, to a person that it hasn't seen before. Let's see.
The gesture of the person at the kitchen counter to the person at the shelf.
So it gets an instruction that it's never seen before, which was, tell me the gesture of the person. Tell the gesture of the person standing next to the kitchen counter.
The gesture of the person at the kitchen counter to the person at the shelf. Is that correct?
So the robot has to understand natural language to get the task from a huge space of possible tasks, and then has to go and execute the task. So it's going into the kitchen, looking at the person at the counter, and then that person is gesturing with its hand up, so then it needs to go and then tell the person, I can't even remember what the command was, standing by the shelf, I guess that's the person. So it's finding the person.
The gesture of the person is raising their left arm.
And so it'll get points for that, for having done the task. It's got 5 minutes, so now it goes back to the starting point and gets assigned another task. So this is the general purpose service robot task. And so I can't remember what the second task was. But in this case, oh yeah, so here it gets the second task now. But you get the idea. We can see what the second task is, but.
Tell me, what is the heaviest object on the kitchen cabinet?
So again, it hasn't heard of these tasks before. It says, what's the heaviest object on the kitchen cabinet? It will then drove to the cabinet. It looked at all the objects. It can pick them up and find the heaviest one, or it can just know by which objects tend to be heavier, and then come back and tell the instructor. So we call this the general purpose service robot task. And so these are the kinds of things that RoboCup at Home encourages, and it's been really inspiring for research. I've also been very inspired by autonomous driving, as many people have been in the robotics community. I had this car in the DARPA Urban Challenge. I've also thought a lot about what the world will look like when all the cars on the road are autonomous. Do they need to use traffic signals and stop signs? Or would intersections look more like this? We actually created this video now more than 20 years ago as a concept of what multi-agent systems could do for autonomous traffic. And then more recently, I believe in this seminar series, actually, there's been a talk about GT Sophie from Ishan Durakar, one of my former PhD students who now works at Sony AI. For those of you who weren't there, I'm not going to talk about that in detail here, but just the quick outline is we had a paper on the cover of Nature almost 3 years ago now, because we created an RL agent that can beat the best drivers at Gran Turismo, which is one of these video games that people take really seriously. They put on they've put in their 10,000 hours to become really expert at it. There was a movie recently about somebody who learned in Gran Turismo and went on to the professional race car circuit. And it's a very realistic simulator. As you can tell by this video, which is Ken Chan, who's an expert driver, drove the same car in the real world, which is down below, and in the simulator, and did his best to sort of follow the same line and do the best he possibly could. And he finished the lap within 1/10 of a second in the simulator of the time that it took him in the real world. And you can see he's like basically it's following the same line. It's dealing with air resistance and tire friction and all the kinds of things that you have to deal with in the real world. And so, our signature event was that we, back in 2021 now, we raced against 4 of the best people in the world at this. And it was using end-to-end deep reinforcement learning. Conventional wisdom at the time was that this would be a task for model predictive control. That didn't work nearly as well. And the car learned things like defensive policies like this. Here, the colored cars are GT Sophie and the white ones are driven by humans. And so here you see the GT Sophie cars learn to make it very difficult to pass itself. So it's a multi-agent interaction domain, not just a drive on the empty track kind of domain. And so this has been the work of many different people at Sony AI. So that's these are the kinds of problems that have inspired a lot of my research over the years. And like I have full hour-long talks on almost any of those topics available online, but they're not the subject today. Today's topic is going to be human-in-the-loop machine learning for robotics tasks, because this is the robotics seminar. And a lot of this is work. I still have 3 things I'm going to tell you that are almost nothing about a few things, and then I'll do the deep dives. So a lot of this work is predicated on the research that was started by Brad Knox in 2008. The TAMR system stands for Teaching an Agent Manually via Evaluative Reinforcement Learning, where we compared it against human learners, against automated reinforcement learners. The sort of initial demonstration was in the game of Tetris, where in the top left corner here, a person is just saying good move or bad move. Green means good move, red means bad move. It started with fully random behavior on a task that reinforcement learning could do fairly well after hundreds of thousands of trials. But here you see, even in the first trial, starting from random, it's starting to do much better than random. It's starting to do things that look. And this is what I forgot to set up. This is one of those videos that I have to stop by myself. They started doing better than random, and by the 3rd episode, so not hundreds of thousands of episodes, it's already clearing hundreds of lines. It has a policy that, based on that human feedback, is able to learn quite quickly. So it learned more quickly, but not as well as the autonomous RL agents. And so then we extended this to combining learning from evaluative feedback with also learning autonomously, TAMR plus RL. We extended it to video input with Deep TAMR in collaboration with Garrett Warnell. And I think Brad has a claim to really being way ahead of his time in sort of this being the first example of what's now come to be known as reinforcement learning from human feedback, which I'm sure all of you have heard about and is playing a big role in the world today. So that's one thing, and then, like I say, extended to Deep TAMR. And we've also done a bunch of work on imitation from observation. So in TAMR, the assumption was that we did have not only the human feedback, but also what actions were taken. But often you just have video demonstrations. And so Faraz Tarabi, also in collaboration with Garrett, introduced the concept of imitation from observation, both a model-based method called behavioral cloning from observation. So basically like behavior cloning, but where you only get to see state sequences, and so you have to figure out which actions were executed by using a world model or an inverse dynamics model, and then using standard behavior cloning. And then also a model-free method that was inspired by Gale. It's generative adversarial imitation from observation, or GIFO, that was using sort of an adversarial learning approach to try to learn a policy that's indistinguishable from the demonstration. And there's a classifier trying to sort of act as the adversary. Again, I'm just giving you tastes of some of this research. And this has also led to some work that we took it to the extreme, also with Brad Knox, on a system that we called imitation from observation. Learning from implicit human feedback. And this is the idea that rather than giving explicit signals like good job or bad job, you can often, if you're in an autonomous car and your passengers look like this, you don't need them to tell you you're doing something wrong. You should be able to infer that from their facial expressions. And similarly, if they're calmly talking to their friends and on their cell phone looking back, then probably you're doing something right. So we should be able to learn from implicit human feedback. So we called this the life problem, and then introduced a first method for this in Coral a couple years ago called empathic, evaluative mapping for effective task learning via human implicit cues, where basically first we watch a person, we learn a person's mapping correlation between facial reactions and good things or bad things happening in the environment in sort of a training phase, and then we use their facial reactions as the reward signal to try to train a policy. And we showed that it doesn't work as well as TAMR, but you can actually learn fairly some interesting things. Okay, so that's the end of the whirlwind part of the talk. I'm now going to slow down a little bit. And after having sort of laid that context, I'm going to talk about two different things in much more detail. I'm going to talk about human-in-the-loop learning for robot navigation, which is the main paper from this. We published in 2022. This is a joint work with Shuisu Zhao, who was a postdoc in my lab and is now faculty at George Mason. And then I will transition into human-in-the-loop learning for robot manipulation that we started working on a couple years ago at Coral. It's ongoing work led by my PhD student Yifeng Zhu, who's on the job market this year. It's in collaboration with Yuke Zhu and others as well. I'll show who's been involved as I go. So, okay, so you can now, if any of that was too fast, now is a good time to zero in and start and focus sort of a little more deeply. So, this first part, human-in-the-loop learning for robot navigation, it's sort of in the context of the classical navigation problem of moving a robot from one point to another without collision with any obstacle. And in many respects, this is a very mature problem. That there are autonomous cars running on the roads. You can have robots in hospitals. There's all kinds of sort of navigation problems that are out there, but navigation is still not a solved problem. In particular, if I tasked you with building a robot that can get from anywhere on the UW campus to anywhere else, from within any room to any building, it's still not there. And one of the problems is navigating through tightly constrained spaces. Where the robot can barely fit in between the gaps. And so that's what we focus on in this problem. But the general classical navigation problem, of course, it has these components. So in this diagram, the robot's at the bottom here. It has some global goal. It has a global representation of obstacles. It could plan a global path. There could be a local goal that it's trying to get to. It has its local perceptual input, a local representation, some motion commands that it's given, and then on the robot there's planners and models. There's a very mature navigation stack, right? And so there's this pipeline that you could talk about like this. And one approach has been to just throw this whole thing out and go end to end and learn, and learn from scratch, from lots and lots of data. And our approach has been to instead say, look, there's a lot of good things about this navigation stack. It actually works very well from a lot of perspectives. And this is just showing that from that previous slide where the navigation stack happens, or maps to the previous slide. But we don't want to throw this out. On the other hand, we also observe that it's fairly rigid in some ways. And so in particular, it breaks down in highly constrained spaces rather than sort of the normal environments like this where it's trying to get between very tightly constrained spaces. The problem is that the classical navigation stacks have to go through a lot more computation. A lot of them are sample-based, right? So they're pushing, sort of sampling a bunch of forwards plans. And so that requires increased computation. But if you use that that higher number of sampled plans out in the open space, then the robot's going to move really slowly. And so it turns out there's no single set of parameters that you could put into a classical navigation stack and have it work everywhere. Either it'll fail in the constrained spaces or it'll work way too slowly in the open spaces. And so that's the motivation. Is that there's this sort of increased computation needed, and also we don't want to throw away the navigation stack. There's already good work on obstacle avoidance and path planning that's quite mature, and we don't want to sort of go to this regime where we need tons and tons of data to even get off the ground. So first, Shuisu's been a champion of this problem. You may have seen, if you've been to ICRA in recent years, we've now had 3 versions of this competition where robots can be trained in simulations. It's called the Barn Challenge. The people who do best in the simulator then are invited to a competition where they can deploy their program on a robot, and we create mazes like this one where the robots have to navigate through very constrained spaces without knocking the cardboard boxes over. And so our approach to this type of problem, we've actually taken 2, and I'm only going to talk about one in this talk. I'm not going to talk about the learning from hallucination work, but I am going to talk about adaptive planner parameter learning, or APPL. And the idea, I've sort of hinted at it already, it's to learn the local planner's parameters and to learn from non-expert humans using different interaction modalities. So that's where the human in the loop comes in. And so the idea is, let's keep around this classical navigation stack, but let's isolate the parameters of this stack as the locus of the learning. And so then keep a lot of the other guarantees. So just, what are those types of parameters? If you've ever worked in, the ROS DWA or, the elastic band packages or any of the standard ROS packages, you know that there's, you probably need to be a roboticist to tune them, right? We're not going to deploy a robot in someone's home and say, before you can run this, you have to set these parameters here, the min vel theta and the Vx samples, and that's just not something we're going to expose to an end user. But it turns out these parameters make a huge difference, and the parameters you want in this type of environment are going to be different than the ones in this type of environment, and in particular in these types of environments as we've shown here, like narrow corridors versus open spaces and things. So to sort of give the overview, and then I'll tell you some of the details, we've sort of looked at different interaction paradigms. So most humans are not robotics experts, but we are all navigation experts. And so when I do put the robot in an end user's home, the person might be able to give some teleoperated demonstrations, like here, where a person's using a joystick to control the robot, or might be able to give corrective interventions, where they watch the robot, but just when it's doing something wrong, jumps in and corrects it. Or at least could give evaluative feedback, like in Tamer, good job, bad job. Right? That shouldn't be very hard for a non-expert to do. And then we also want to allow for the robot to do some reinforcement learning, maybe not in your home, but before it gets to your home. And so these are sort of the four different sort of variants of adaptive planner parameter learning that we've explored, and I'll talk about each of them now. So first of all, one thing in common with all of these different modalities of APPL is that in navigation language, you can think of this as one sort of depiction of the classical navigation stack. You have a map, you have sensors, there's some goal, and out is going to come some action. So this is like the move base diagram from ROS. And so what we're going to do is treat the navigation stack as a black box. We're going to look at the map and the sensors, but then learn the parameters that go into this black box that govern its behavior, and then out will come some actions. So that's one way of looking at it in navigation language. In reinforcement learning language, the way you can look at it is, here's the standard reinforcement learning diagram, where you're given some state and out comes some actions into the world. So this is what you do if you do throw away the navigation stack and do sensors to pixels actions or policies. But instead, we're going to learn a parameterized policy where the environment is the motion planner and the world combined, and out from the policy that we're learning is the set of parameters that I showed on the previous slide, and then that indirectly governs the next states and rewards. Okay, so that's the idea of APPL, adaptive planner parameter learning in general. The locus of the learning is these parameters, not the actions themselves. Okay, so now let's talk about how can we do this from, please.
How do you think about the trade-off from like the end-to-end thing to the more parameterized thing? Because like you're losing expressivity, but you're gaining guarantees. Like, are there particular problems where you might want to, how should we think about when to do what?
Yeah. So not to be. I don't mean to be snide about this, but if I wanted to publish a paper, I would do it end-to-end, and if I wanted to deploy a system in the real world, I would do it this way. Like, I mean, the end-to-end learning it's fascinating to see what you can do, but it's still like, the fact is it's not as good as if you take the classical navigation stack and even unmodified. Like if you're going to put the robot in somebody's home, first of all, you can't do the end-to-end learning in their home, and if you did it somewhere else, it's not going to work in their home. You're going to be able to publish a paper. It's going to be neat. It's going to create some videos. It's doing better than maybe people would have expected. But if you're a practical roboticist, I would advise this. Yeah.
Do you change the parameter like per state, or is it per environment? Like, do you?
So hold that thought. That's exactly where we're going right now. Good. Yeah. Any other questions? Good. So So then I said, so now how do we take this APPL, this adaptive plan and parameter learning, and do it with from human interactions? So we now have this sort of policy set up, and there's going to be some interactive data, and so the sort of high level, very high level pseudocode is that you're going to get some human interaction and a space of possible parameters and the navigation stack in. You're going to learn the parameter policy from the human interactions, and then you're going to basically construct the metastate from x and theta and sort of loop through this. So that's sort of what this diagram is saying. And the thing that's going to differ across the different variants of APPL is what kind of interactions you get and what you do with them. How do you learn from them? So the first thing we did was APPL from demonstration, which we called APPL-D. And so the interactive data here is a person using a PlayStation controller to remote control the robot. And to answer your question, the first thing it does is it learns a context predictor, which is basically what type of environment am I in? Am I in an open space? Am I in a corridor? Am I in like a maze? And then once, as a function of that context, you're going to learn a parameter library, the parameters that work for that type of environment. And so for each context, we use behavior cloning to construct the element of this parameter library. And so you can think of it as your sensor data comes in, and then the context predictor is going to be as a function of x and theta. You're going to get some motor commands. Actually, this isn't showing the context predictor yet. This is within a particular context. And then the behavioral cloning is learning the parameters from the demonstration using supervised learning with the loss you would expect. Just basically, try to come up with the parameters that lead to a trajectory that's as close as possible to what the person demonstrated. And so I'll show the context thing in a second, but here's a video of it. So here's conceptually there's 4 different environments. Here's the default parameters that come with the DWA stack. Here's the robot after learning, moving, using different parameters for different environments or different types of environments. So it's, noticing that it's in the corridor, and so now using parameters that do lots and lots of path sampling and slow it down. Whereas I think in this case with the default parameters, it failed. We had to actually manually reset it because it wasn't sampling enough paths. So there was a manual intervention to have it start again. And then when it gets to the end of this corridor, it then recognizes it's in the open space context and speeds up, much less sampling, and is just able to go, whereas the default parameters are still crawling along. Okay, so, oops. Oh yeah, so here's the slide I predicted. So I skipped. The context predictor is basically taking the state in, and we're doing automatic sort of segmentation of I think we used CHAMP, which is sort of something that Scott Neekum did for context prediction or segment trajectory segmentation, where it's looking into different qualitative types of environments based on the local sensory data. And so it doesn't have semantic labels. It just learns that there's one context here, one context there, a different one there, and a different one there. We know that these correspond to curves and obstacles and corridors and open space, but it just gets this from the demonstration to learn its context predictor. Good, so that was APPL-D. Then we said, okay, but demonstrations might be a little too much to ask for. What if we have a policy that's good most of the time? Maybe now, a person would just have to intervene. So instead of giving the just the joystick command, a person now sort of taps in and says, "I'm going to take control," and then taps back out and says, okay, you can have control again. So sort of like an intervention, only when necessary. So we call this APPL-I, or Adaptive Planner Parameter Learning from Interventions. And so our observation here was that there were sort of, in this type of domain in navigation, there were fundamentally 2 types of interventions. What we called type A interventions, the one where the robot does the wrong thing. It's about to run into the wall. The person says, no, that's bad. Let me back you up to where you were before and show you what you should have done. That's a type A mistake. or intervention. A type B intervention is you're doing the right thing, you're just doing it way too slowly. Let me tap in and set the velocity. And so we categorize them into those two, and then use that to basically have use some of these, the parameter libraries are learned from the demonstrations in the contexts that the people labeled as type A or type B. So basically, you first, and then it's learning a function that says, is this a place where the person was confident in what the robot was doing, in which case you can just use the default behavior, or is this a place where the person was not confident, and then you need to take a learned behavior from that demonstration. So that's the intervention one. And then finally, the one that's closer to tamer, adaptive planner parameter learning from evaluative feedback, or APPL. Apple E, I guess we said. And this is now, the intervention is just thumbs up, thumbs down. And so, a person's watching the robot, and I think the way we did it was the default was good job, and we just had to tap in when we tap the button to say bad job. And so now we have some. In this case, we had a discrete set of possible parameter libraries. These were learned from Apple D or back in the factory or whatever, and we're trying to learn a function that says, if I used these parameters, would a person give me positive or negative feedback? And then you take the one that use the parameter library that you predict would have the highest likelihood of a person saying good job. And this was sort of fundamentally the way tamer worked as well. And so, in this case, we would collect a feedback set from the person. We would train the feedback predictor using a loss function of is the person going to say good job or bad job, and then deploy the parameter policy on the robot. Yeah.
Out of curiosity, what's the order of magnitude in terms of how often do these training need to happen for the robot to behave satisfactorily?
So so this is now, I forget how many. All of these were from very small numbers of demonstrations. We did have the benefit of this all happening during the height of COVID, so the atrium of our building was wide open, and we could set up in the middle of the day and run it, take over the whole thing. But it was handfuls of demonstrations. This was all within the I don't remember the numbers off the top of my head, but it's in the paper how much we took. And the idea was the kind you could imagine, the scale that you could imagine a person doing in their home. And certainly, this was done on real robots. So, it was a PhD student or a postdoc doing it. So it's not millions of examples for sure. It's more like tens to hundred. Okay, and then finally, I said that we also want to be able to learn from pure reinforcement learning. This is going to have to happen in the simulator, because this is where in the pure reinforcement learning setting we do need lots of examples. And so now there's no human interaction, and that was what motivated this, the barn data set, where we created we had 300 different environments that are rated from the easiest to the hardest based on level of clutteredness, and now we're just learning a policy network. This is more like end to end, but we're learning we're optimizing a reward function that has 3 components, one for did you reach the goal, one for are you making progress towards the goal, and one for how close are you to an obstacle. And then learn again, still learning the parameters though, not learning end-to-end pixels to motors, learning the parameters that will lead to the highest reward over time. And so that's the overview of this human in the loop learning for navigation with all these different modalities, and the high level objective, or the long, and this was the culminating paper, was putting these all together with the idea that you could do APPL in the factory before the robot gets into the real environment, but it's very general. And then a person could either do demonstrations or interventions or evaluative feedback, and you can learn from any of those to improve the policy. And then possibly even you could imagine that happening during the day, and then at night while everyone's at home sleeping, you could take what's been learned during the day and go through another iteration of APPL with maybe a different reward function that's learned from what the people have indicated. And there's a bunch of research in my lab now, and Brad Knox is still there. We're working together on learning reward functions from human preferences. I'm not going to talk about that more in this talk, but it's sort of very tied into this. Yeah, please.
So I'm not an expert with like classical navigation stacks, but so this robot here seems like a track robot, like 2 tracks. Like, how do these like classical navigation stacks work when you have like more complex environments that might have like stairs or something, where it's not like easy to just like go up to 2nd floor or something? Like, you might need like a legged robot or something like that. Like, does this?
Yeah, they're sort of orthogonal. There's the how do you move, and there's the where should you move. The classical navigation stack is basically doing the where should you move, and the fundamental sort of underlying data structure is a cost map, which basically says which parts of the environment are better to move through and which are the ones that are not good to move through. And those could be robot dependent. If I'm a tracked robot like this, I would put a very high cost on stairs. If I'm a humanoid robot that can walk on stairs, I would put a lower cost on stairs. And so like, and then once you have that cost map, you plan a path that has guarantees of not bumping into the high cost regions and things like that. Yeah.
Related. Like, do you just learn on are you tuning the local planner, or?
This is all local. Right,
Local.
so this is completely beneath, so in that sort of high level diagram I talked about, this is not doing the global path, this is doing just the local path. And yeah, you could combine it with A star or with any of the other types of sample based PRM or kind of things to do the global path. That's a good point. I should have said that. Yeah.
In these setups, how stable was the perception for your experiments?
This was pretty. Yes. Well, I don't know what you mean by stable, but these were all laser rangefinders. These were distant, sort of distance-based sensors that were pretty accurate. So like it could tell whether it's in a constrained space or not. Is that what you're asking?
Yeah. But if you're in some more complicated environments, say outdoors, and there's like a lot of flickering obstacles because you're not always able to like get the sensors correctly. Like basically, there's a lot of noise in perception.
Yeah.
Like, how do these algorithms fare over there?
That's a good question. We haven't done the that sensitivity analysis. I mean, I would treat that as sort of a separate problem. The world modeling and the situational awareness as being sort of prerequisite for this. But so if the robot has no idea whether it's in a cluttered space or an open space, then the advantages of this are going to fall away. You probably need to take the very conservative approach in that case and use the parameters that move very slowly and carefully and do lots of sampling. Yeah, that's a good question. I should say, because I know there's people here who are in Byron's lab, and we have a paper recently that I'm not going to talk about here, but was with Garrett and Joydeep Biswas and a student, Louisa Mao, a system called Pacer, which is basically using this cost map kind of idea, takes as input the robot's current sensing, and then also just a couple of pairwise preferences over which terrains are going to have high cost versus low cost. So we actually take 3 of those pairwise preferences, and they can be over terrains that the robot has never seen at training time. And the robot is able to, at deployment time, with no further training, just based on those 3 preferences, to sort of build a cost map and use the classical navigation stack to move through that environment based on those sort of preferences over unseen terrains. And so that's very recent, but it's out on arXiv if you want to find it. That sort of talks more about this. How do you do the cost map type planning and take human preferences, but in completely new environments. But
related to a question,
yeah.
What is your perspective on sort of label sensitivity, label noise? And obviously, like one way to analyze that would be to have some model of intervention and then have the optimal policy and then compare against that.
Yeah, I mean, sort of the workhorse sort of method here is in learning from human preferences is the Bradley-Terry model of where you assume that when people are giving preferences, there's some probability function that they're actually giving the correct labels versus the incorrect labels.
No, I mean, even here, like you can do this analytically, right? Like if you have an optimal policy and you have some model of intervention, maybe you decide what the model of intervention is.
Right.
Like what unhappiness is. Maybe you decide that the state action value function has to be beyond a particular threshold. At that point, they're unhappy. Then one can have I guess like a procedural analysis of how.
So that would, I guess, be if the impetus for interaction is from the robot asking for help.
No, here the human.
Here we're asking the human to do it, so we
But what if
basically
the
just
humans-
trust the human to decide when they're
What
unhappy.
if they suck at it? Let me rephrase that. What if they were noisy with it?
Yeah.
I mean, they're never going to suck at it, but they'll be noisy with it, right?
Yeah.
And they may have an internal model that you don't know.
Right. So I mean, we didn't deal with that explicitly in this work, but we do deal with that explicitly in the work I have recently with Brad on learning from human preferences, where there can be explicit noise in there. Of course, the more noisy it is, the more the sample complexity goes up, the more data you need to be able to do relatively well. But we definitely explicitly model that people are going to be noisy in their preferences. In the sort of learning, in that work, we're basically learning reward functions from preferences and then doing sort of inverse reinforcement learning style stuff. And we model that it's probabilistic what type of feedback people give.
Here
in this work, we didn't do that. Here we are assuming correct that all of the human input was noise free.
And it seems like evidentially it also seems to sort out, right? Like it's
Yeah.
working in the real world.
With high quality, good feedback, that with we were more focused on, let's make sure it's feedback that a non-roboticist could give, but let's assume that it's going to be good feedback. Then yes, now in the work I hinted at, the empathic work, where we're learning from implicit human feedback, the facial reactions. There, it was definitely not a perfect signal. We were so there we were assuming that it was a noisy signal that you're getting implicitly. But all this work in the APPL paradigm is explicit feedback, and we assume people are good at giving explicit feedback. But it's a good question for offline. So I can come back to it, but let me go on just in the interest of time. I'll shift gears to the second deep dive. So that was one, the human-in-the-loop learning for robot navigation. Now I'm going to talk about this human-in-the-loop learning for robot manipulation. This is, as I said, it's the PhD thesis, part of the PhD thesis work of Yifeng on the job market this year. Aris Ray is a very talented undergrad working with us, and it's joint work with Professor Yuke Zhu as well. There's a series of work in this space, but I'm going to talk to you about a particular paper called Vision-Based Manipulation from Single Human Video with Open World Object Graphs. And so now, as I said, we're in the manipulation domain here, robots like this one. And the idea is that robots, all robots operate in a relatively low data regime. You can't get millions and billions of interactions in the real world, although I guess physical intelligence is trying to go sort of prove that wrong, that you can get lots of it, and we'll see how that works out. But the idea is, hardware is expensive. It's complex evaluations in the real world. And so, a lot of people have taken the idea of let's learn from human data, including people here at UW. There's fantastic work in this space. And a popular paradigm is imitation learning with some demonstrations. And traditionally, a lot of the demonstrations have come from teleoperation or remote control devices. But that can be physically demanding. It can be hard to control a high degree of freedom robot with any of these devices. And so you have to have high proficiency at doing that. And so the motivation for our work here that I'm going to talk about is that we want to learn from video data. Video data that you could just take on an iPhone. And so that's easy to collect. It's readily available. It could be from YouTube. It captures human sensory motor knowledge of context-rich information. And so there is a lot of work sort of in this space, but we have a particular niche. So there's some work that's that pre-training from lots and lots of data. But then when you get a new task, you need some additional robot demos in the testing domain, which is basically based on lossy compression of all of this, lots and lots of video data. And so it's it's not super efficient with the data. We're going to sort of take the flip view and say, but it's trying to learn a generalist policy. We're instead going to say, for every skill you want to teach the robot, you need a demonstration, but you just need one demonstration. And then we're going to milk as much as we possibly can out of that single demonstration, that single video about the skill. And you don't need any additional robot demos after the first one, and so we can scale up skill learning. But again, when you want to teach a new skill, you're going to need one more video. You'll see why as I talk about this. So yeah, I'm already motivated this a little bit. There is a lot of related work in this space. There's sort of the one-shot imitation learning, but that relies on lots and lots of meta training first, or additional simulation at test time. There's video pre-training that's sort of that lossy compression kind of approach and needs additional robot data for the testing tasks. And there's visual imitation from single video demonstration, but usually assumes that you've seen all the objects ahead of time, that it's known objects. And often requires extra exploration at deployment time. So what we're looking for instead is a single human demo, actionless video, and a generalizable policy, one that'll work in lots of different conditions. And so we call this open world imitation from observation. Again, sort of that same, I talked about imitation from observation earlier for Oz's work. Similarly, we're not going to get action information, we're just going to get video or state information. And so the insight is that that the demonstration we get, the single demonstration, is moving objects along trajectories similar to the ones shown in the video demo. Or at deployment time, we want to move objects along trajectories similar to the ones shown in the video demo. We want this to generalize to different object layouts, no predefined number of subgoals. And so to do this, we're going to use an object-centric representation. That's a buzzword, but I'll tell you exactly what I mean by that in a second. To track object motion in the video and localize objects at test time. And to allow us to deal with any number of subgoals, we're going to do automatic segmentation of the video demo to identify keyframes and handle arbitrary length video demo. I'm going to go into more detail on all of this. This is high level. So the system that Yifeng created is Orion for open world video imitation that takes in a single video demonstration for a skill, builds this object-centric representation, and then works in diverse test environments at deployment time. So again, single human robot demonstration for each task. And by diverse test environments, I mean that the objects can start in different spatial layouts. There can be different visual backgrounds from the demonstration, different camera angles from the demonstration, and there can be even new object instances of the same class at deployment time than in the demonstration. If I'm using a mug, it doesn't have to be the same mug. If I'm using a marker, it doesn't have to be the same marker. So how does it work? The pipeline of Orion is that, and it puts together a lot of different components, but it's using vision foundation models to extract object-centric information. So it's basically taking this. Here's the video of the object being moved from one place to another with a visual object segmentation model. That's a pre-existing package, so it's able to sort of segment out the objects and track them over time. It's able to follow the point flows, so there's a key point motion tracking with a system called Track Any Point. So that's the output of this video, where you can sort of see the points of interest following some kind of trajectory. And then there's also hand tracking. So we assume that the demonstration is from a single hand in the video, and we can track that hand, segment it out and track that hand. Good, and so that's how we're using some of the vision foundation models that exist. The representation we use is an open world object graph. So basically, tracking at different key points through the demonstration, what are the contact relationships or spatial relationships between the objects of interest that are defined, that define what the demonstration is about, and the person's hand. So, for instance, it might say if the object of interest, I'll tell you how we get the objects of interest in a second. But if the object of interest is this sort of, I guess this is a llama or whatever it is, and this potted plant, and the person's hand is also an object of interest. At this point in the demonstration, there's no contact between them. Then there's a time when the hand picks up the object, so the contact relations change, and then there's a time when the object is touching the other object, and so each of those becomes a keyframe during the demonstration. Oops, I missed. And then at test time, the robot policy is going to generalize this to the same task under different conditions. Again, more details are coming. So what are the assumptions? First of all, we assume that it's RGBD video of a person taken with a stationary camera. It could just be an iPhone with a depth, with a depth sensor on it. We're trying now to get rid of the D requirement to just do RGB video, but in this talk, it's RGBD. The object interaction in the demonstration is also always with a single hand, and it contains a manipulation sequence where the contact relations change among task-relevant objects and the hand. And then there's minimal annotation, which is that a verbal list in natural language of the task-relevant object names given by the demonstrator. So if the demonstration, if the task is defined by the water bottle where it ends on the table, then I'll just have the string water bottle table, and then the demonstration. So again, I'll show examples of this. But then, so you get this RGBD video, and you get the text description, like the small red block and the boat body. Those are the things that you care about. Out from that will be the keyframes using keyframe trajectories, and then the object, the open object graphs that say what are the different contact relations. By the way, this automatic segmentation is using a sort of a kernel-based method where we're using the key point tracking and when the velocities of those key points change to be sort of where the likely keyframes are. So that's how we can do this for any length description. So we have this, the video, the text description. We identify the keyframes and generate the open object graph. We're using key point tracking to reconstruct the hand from the images, to segment out the objects that were described by the text, and then to back project the point clouds into where they are in 3D space. From that, we'll track the object motions with sampled keyframes, and then track where the object went in 3D space. So, and then from there, we'll get these open object graphs, which track the thumb and index finger distance, the object point clouds, and the key point trajectories. And so you might have a node for the hand, a node for each of the objects, and then different edges between them for whether they're in context, whether they're a part of relationship, or whether there's no contact. So that's the sort of abstraction, the object-centric representation. So then at test time, or at deployment time, we synthesize the actions by now looking at where the task-relevant objects are in the new image. Might be a completely different spatial relationship, but there's still a red block and a boat. We then retrieve the OOGs from the demonstration, and then we take where the objects are currently and where they were in the demonstration, and then predict the trajectories using global registration transformation. So basically, we're saying that the point transfer, we transform what the trajectory was in the real world to what it's going to be in the current world, based on having sort of the same shape but different start and end points because of where the objects are right now. And then from that, we can optimize the action sequence in SE3. That's sort of just taking this point flow and saying, using an inverse dynamics model to say what should action would give us this. So here's the sort of punchline video. How do I play this? Yeah, there we go. Here's the video demonstration defining the task. So just a single demonstration of the person doing this. And then here is, in a different scene and spatial layout, the robot executing that same task. And the text in this case would have been small potted plant and llama or potholder or whatever. And so we can start it now with the potted plant starting on another object. That doesn't matter because that one is not one of the ones that we were told to pay attention to. We can change it to a completely different background. That doesn't matter because it's still the same objects that are relevant. So it's still able to do it. Doesn't work every time. I'll show you when it doesn't in the past. But here's a new video demonstration that's longer horizon, so 2 different objects. So now again, it's going to be able to take it to different starting conditions, different lighting conditions, different backgrounds. In this case, the text string would have been the descriptions of both of those objects and the boat. Those are the things that we care about. Can work in extreme lighting conditions. Just because of the generalization of these segment anything model kinds of things, it's still able to bring out the objects and it's also able to work to new objects. So we just said that it's the mug that you care about in this video demonstration, the mug and the placeholder. Here it's a different mug, but it doesn't matter because the models are able to take that text description and find the mug and segment that out, even though it's a different looking mug. So those are that's sort of and then this is just more examples of the mug going onto the placemat where it's different mugs, different backgrounds and all. In the paper we evaluated Orion on 7 different tasks, that are shown here, and got the human videos and got the text descriptions of what you should care about, and then the policy evaluations. As I said, they didn't work all the time. The success rate was in the 60% range normally, or generally, but the failures were sometimes sensory, like mistracking or misgrasping. The grasp doesn't always work perfectly, or the contacts that you were trying to achieve didn't work. But it generalized all of these cases from just a single case to a relatively high success rate. But not perfect. There's still room for improvement here. So future work, like I said, we could try to get rid of that depth constraint in the RGBD from the demos, because then you could just use YouTube videos. We're already working on higher degree of freedom robots. So using this Furrier robot, we actually have a paper that was an oral at Coral last year called Okami. This is with Aris Ray and Yifeng, where it's using the humanoid robot with a more complex grasper, and also dynamic or forceful manipulations as opposed to these quasi-static tasks. So that's Orion. Again, single video demonstration with diverse test environments, efficient cross-embodiment transfer of manipulation skills, and an easy, user-friendly human-to-robot teaching interface. And this is what I wanted to show you with regards to human-in-the-loop learning for robot manipulation. So I'm happy to stick around for questions if people want to. But again, just as the reminder, I've talked to you sort of about a lot of human interactive learning, going back to Brad's original work now, getting close to 2 decades ago, but really focused in on these 2 pieces of work: the APPL work, adaptive planner parameter learning, on human-in-the-loop learning for robot navigation, on the Orion work on human-in-the-loop learning for robot manipulation. And with that, thank you for your attention.
I will MC the questions for the next 3 minutes until we finish the video stream. After that, Peter will be around. He's meeting with me, but I'm happy to let you all take some questions with him. So official questions for 2 minutes. Go ahead.
So just curious, how does this stuff that you research, how do you see that transitioning into different parts of reinforcement learning? Where do you see future of this from?
I still got this.
Oh, you got it.
Yeah. I think, that's a great question. I mean, I think I'm a big believer in not throwing out the baby with the bathwater. I think to use the parts that when it comes to robotics especially, to use the things we already know how to do and to the well-engineered components, to use those and make the locus of the learning the parts that we don't know how to do. And both of these tasks, I think, sort of give sort of a sense of that. In APPL, we were learning just the parameters, but keeping most of the navigation stack. Orion is imitation learning, not so much reinforcement learning, but same thing. It's using lots of components that already exist and trying to learn the parts that we don't know how to do, and in as much as possible. And I think that's important. And then the other theme that I tried to get across here is allowing there to be human input into defining what it is the robot's doing in reinforcement learning. We've learned that it's really hard to create good reward functions that'll work with limited data. It's not that hard to create a perfect reward function if you're willing for it to be very sparse, like just get to the goal if it's a goal reaching task. But if you want a more dense reward function that supports learning with less data, it can be very difficult to find the right one, and allowing people to give their preferences in different modalities in a sort of easy user interface, and to try to, as we were talking about with Sid a little bit, embrace that people aren't going to be perfect in giving that feedback and figuring out ways to induce what the reward function is. I think that's an important direction.
I think we're at time, but
I'll take more
we'll
questions if
stay
people
on
want to
to
stick
take
around.
questions.
If you want to stop the stream, go for it. But I'm happy to keep answering for a bit.
I'll ask the stream gods. Should we continue? All right, we'll just keep going.
Sure.
For Orion, 2 questions. One, did you ever try using robot videos or cross-embodiment robot videos instead of just human? And then also, like, do you think you could ever, like, maybe use it to bootstrap, like, a larger data set and then train, like, an actual imitation learning policy on that larger data set?
Yeah. I mean, I've done work that does use these larger data sets. And the idea for Orion is to try to really, like I said, milk as much as you possibly can out of individual ones. Yeah, I think if you have more data, you can use more data with different kinds of methods. For cross-embodiment, yeah, I mean, the only assumption here is that there's a single hand doing the demo. That's an assumption we could probably relax, and it doesn't have to be a human hand as long as you have a hand tracker. So, if you had a robot that were doing the task well, as long as you can track their hand, you could use this method without change. Yeah.
So with Orion, you seem to take the approach, like you said, like you try to milk like as much you can get from one demonstration. But you also seem to think about seems like you think about how can you deploy robots in the real world. And so with the real world, you probably have like kind of open-ended like instructions. How do you imagine like this like Orion kind of paradigm or other algorithms like playing into that, where like will you like have to like load in like a past demo and like do some kind of like retrieval, or how are you going to execute like open-ended instructions, I guess?
Yeah, so we're doing some work on that. A lot of it, I think, comes down to sort of tying to that previous question of like taking an instruction, inducing what the corresponding reward function is, and then it depends what you have what you have available. If you have a simulator available and lots of time, then you can turn the instruction into a reward function and do reinforcement learning. If you don't have a good simulator and you have to do it sort of one shot, then you might have to take that human instruction, and we have actually a paper under review right now which would sort of take that human instruction and try to imagine what the demonstration might look like, and then do something like Okami related. You could do that. That's something that vision language models might allow you to do. So I mean, I think there's all kinds of possibilities. Yeah.
For the RGBD video, the single hand demo, were there demos where the IK didn't work out on the robot, or were there occlusions, and did the demo need to be like exaggerated? Were there any other?
Well, you saw examples of the videos on there. They weren't really exaggerated. They were clean in the sense of there was a hand that we could recognize and segment out. The motions were not unnatural. It was just pick up the object and move it, and then we can do the point tracking there. So I mean, we tried to sort of be reasonable about what the demos would look like. There was no sort of markers on the hand or anything like that. It was just and it was really literally an iPhone that took the videos. Just a mounted still camera that could see the scene and then do the demo and get those verbal tags of what you should be segmenting out.
Were there any demos that just failure, like in the failure?
Yeah, I gave the data of like sort of the failure cases. It only worked like 60% of the time, and sometimes it was because of just missed motions. But then there was like it said, I think the object contact relations weren't possible to achieve. That was a small percentage of them, but I think there were some that we couldn't do what the demo did with the hand. Yeah.
Sorry. In the spirit of like using things from robotics that we know how to do well, in the Okami pipeline, did you try to use motion planning for the like final one?
That's sort of when you go from that point flow to the actual motor commands. That is a rudimentary form of motion planning, right? We're going from a start point and a trajectory to what are the motor commands to the robot that will make the end effector follow that point flow, and so that's a motion planning module.
But if there were like other,
if there were obstacles, right? So we're not doing that. That's sort of another answer to this question. Is like the assumption is that it's that the hard part of the task is not how do you move the arm through a bunch of obstacles without knocking anything over. If there were like a house of cards around and you had to avoid that, Okami doesn't explicitly deal with that. We're not doing complex motion planning. You could imagine doing that, though. Then you might have to segment out, or you might have to add, something like, the things I care about are the boat, the mug, and the house of cards. And then from the demo, I would have to recognize that that the demo is avoiding the house of cards, and then you might be able to, make that a high-cost region and do motion planning around it. We haven't done that. It's an interesting idea, but yeah, in this case, all the demos are in sort of open space. Yeah.
Question back to Apple, like you have different method, right? They have reinforcement learning and back to human. Like, is there like a point like the robot realizes better than human, right? Like in the reinforcement learning environment, the robot realizes this cost is better than human. You stop learning from the human or something.
So in Apple, we don't really have a mechanism for that. It's more of a behavior cloning or imitation learning kind of setup. Inverse reinforcement learning allows you to do better than the demonstration, but behavior cloning is sort of fundamentally limited by the demonstration. No, so we don't have something that would say, stop telling me what to do, I know better than you. But yeah, that's an interesting direction as well.
I had a question on the registration. What was the method that you used for registering the trajectories for the manipulation?
There's a track any point method, TAP, that was basically watching turning the key points into point flows. That was an existing package.
Okay, so I guess then the question is, how do you deal with your task is to move a block from a surface onto a table? What if the surface is like higher in one case and lower than the table?
That doesn't matter as long as we can identify the start point and the end point. Then we're constraining the trajectory to have the right start point and end point, and then trying to make the shape as close as possible to the demonstration. But we anchor the start point and the end point. So if they're higher or lower, that won't matter. Maybe we should probably cut off, right?
I think we'll stop right now the official video stream, but Peter is here, so please do ask your questions.
Thanks, everyone.
Formally. Thank you so much.